بسم الله الرحمن الرحيم. اليوم نبدأ محاضرة رقم 16 في إجراءات إشارية رقمية في الدي اس بي. راح أتكلم اليوم في موضوع صغير، يعني هو مش كتير كبير، اللي هو relationship between the discrete time Fourier transform and the discrete Fourier transform. So محاضرة اليوم هي relation between the discrete time Fourier transform, which is known as x of ej omega, and the discrete Fourier transform, which we call it x of k. So what is the relationship between the DTFT, which is x of ej omega, and DFT, which is x of k for k between 0 and n minus 1. Okay? Okay, I'm gonna take an example first and look at it with you. Let x of n، راح اخذ example نتفرج عليه انا وياكم، نتفرج عليه سوا ونشوف شو العلاقة ما بين ال DTFT وال DFT مع بعض. So I'm gonna take x of n, which is equal to 1 to 0, and then this is our very famous sequence now. X of n تساوي or equals this value. So what is x of ej omega of this one? We know that this index is 0, 1, 2, and 3. So x is 1 plus 2 e to the minus j omega. The 0 has no value, which is 0 times e to the minus j 2 omega, plus the last one is 1 times e to the minus j 3 omega. So x of e j omega equals to 1 plus 2 e to the minus j omega plus e to the minus j 3 omega. So this is our x of ej omega. And as we mentioned before, this x of ej omega is a continuous function in omega. Continuous, this is for omega between minus infinity and infinity. Continuous function in omega and periodic with a periodic with period of 2 pi. Yeah? So this x of ej omega is continuous in omega from minus infinity to infinity, continuous in omega, and periodic with a period of 2 pi. Okay, what I will do here, I will evaluate x of ej omega at, I'm going to look at, so let's say that this is x of ej omega, magnitude and phase, and I'm going to evaluate this from 0 up to 2 pi with 4 samples between 0 and 2 pi. So I'm going to take this to be 2 pi k over 4, and k goes to 0, 1, 2, and 3. So the first one will be at k equals 0, So this is your first sample. The second one will be 2 pi over 4, then 2 times 2, 4 pi over 4, and 6 pi over 4. Okay? So we're going to take the first one here, the second one, so you will have 1, 2, 2 pi over 4, which is equal to pi over 2, 4 pi over 4, and 6 pi over 4. 1, 2, 3, and 4. 4 samples of this x of ej omega. And let's evaluate x of ej0. So the first one is 0. So you have 4 different frequencies. Omega 0 equals 0. Omega 1 equals pi over 2. Omega 2 equals to, which is 2 pi over 4. Pi. Omega 3 is equal to 6 pi over 4, which is 3 pi over 2. So you have 4 different frequencies. Those frequencies will be applied to x of ej omega, and we will find the values. So x of ej omega, you apply the value here. It's 1 plus 2 e to the j0 plus e to the minus j0, e to the minus j 3 times 0. So it's 1 plus 2 plus 1, and this is equals to 4. Okay? So this is the first value. The second value is, I'm gonna take those from here. X of ej pi over 2. So this is 1 plus e to the 2 times e to the minus j pi over 2 plus e to the minus j 3 times pi over 2. So this is a complex quantity. E to the minus j pi over 2 is minus j, so this is 2 minus 2j. And this one is minus 3 pi over 2, which is 90 degrees actually. So it's plus j, so you have 1 minus j. And the third one is x of ej pi. So this is 1 plus 2 e to the minus j pi plus e to the minus j 3 pi. So this is equals to 1 minus 2 minus 1. And this is equals to minus 2. And the last one is x of ej 3 pi over 2. The third part here. So this is equals to 1 plus 2 e to the minus j 3 pi over 2 plus e to the minus j 9 pi over 2. So this is 1 plus 2j minus j is equals 1 plus j. Okay, if you look at those and you go back to x of n and evaluate for this x of n, what was x of k? X of k of this sequence was equals to 4, 1 minus j minus 2, 1 plus j. It's the same values that we got for the sampled version of x of ej omega. So basically, x of k is a sampled version of x of ej omega. And you look at those samples here, which is equal to 2 pi over n. This is the period between every sample. As if when you look at x of k, actually you are looking at x of ej omega for the period between 0 and 2 pi. 0 and 2 pi, but it's a sampled version. And this is very clear. X of k, as a definition, was equal to the summation of x of n e to the minus j 2 pi k n over capital N. And this is what we have done here, 2 pi over 4. That was the sampling, 2 pi k over n. This one here is the sampling of the period, the sampling of the period from 0 to 2 pi by so many points, which is equal to 2 pi k over n, where k goes between 0 and n minus 1. Okay, so if you do this, then x of k and x of ej omega, they are, they represent the same sequence in frequency domain. This one is continuous, but this one is discrete, and it's a sample version of this one. Okay, so this is one of the things that we would like to show you. So we can put this in formal manner. And put it in, so x of e j omega at omega equals 2 pi k over n equals to the summation from n equals 0 up to n minus 1 x of n e to the minus j 2 pi k في n over capital N for k between 0 and n minus 1, and this is actually equals to x of k for k minus 1. Okay, then we will move to one idea which is very important here, is can I compute this x of ej omega using computers? Now you have to calculate, when we calculate x of ej omega, x of ej omega has to be done numerically. Then you apply it to the computer with a very dense values, or then very dense values of omega, so that you have a continuous function of omega. But can we do it using the discrete Fourier transform? Let's look at the relationship of those two together. So we would like to see numerical computation of x of e j omega using x of k. Okay? Can we do this? Yes, we can. Let's see how we are going to do that. Okay, so we wish to evaluate x of ej omega at a dense grid of frequencies omega sub k, which is equal to 2 pi k over m, where k between 0 and m minus 1, and m is much greater than n. Okay, what does that mean? It means that we would like to evaluate x of ej omega on a continuous range of frequencies. We cannot do that in computer, so we do it in a very dense grid of frequencies. I mean, if we would like to evaluate x of e j omega over frequency from 0 to 2 pi, so what we usually do in computer, we take this period and we divide it into very small values. So you sample it and you take so many points inside. So the number of points here is m points, from 0 up to m minus 1 points. Okay, so you have m points. The period between successive points is 2 pi over m. This is the period. Okay, So as if you are saying that you have 2 pi k over m, and your k is between 0 and m minus 1. So these are your w k's. So my w k's will be 2 pi over m for k between 0 and m. Whenever you have a point, let's say 100, so this is 2 pi times 100 over m. It's the number 100 point, or the 101 point that we will get at this range here from 0 to 2 pi. And this is what we mean by a dense grid. A dense grid means that you have so many values so that your resolution will look like as a continuous function. Okay, so this is what we mean by x of ej omega, and the definition of this one is x of j omega k is equals to the summation for x of n. Notice that x of n still is an endpoint, so this is from n equals 0 up to n minus 1. Now the frequency wk or omega k will be substituted inside, so this is e to the minus j omega k n. And if we substitute omega k, what is omega k equals? So this is the summation from n equals 0 up to n minus 1, x of n e to the minus j 2 pi k times n over m. Notice here it's m, not n anymore, because you are doing x of e j omega k. Okay? So this is not 100%. This is not x of k actually. It's some variation of x of k. Okay, I'm going to define a sequence now. Define a new sequence x extended of n. So x extended of n is equal to x of n, the original x of n for n between 0 and n minus 1. So the same sequence. And it will be 0 padded for n greater than or equals capital N less than or equal n minus 1. So if you have a sequence, you extend the sequence by zeros. So you augment zeros, number of zeros, until the whole sequence, the new sequence, has a length of m from 0 up to m minus 1. So x extended of n is of length m. The extended sequence has a length m. The original sequence with 0 added at the end until you reach the length of m. Okay? So what will be x extended of k? Notice, I'm not going to find x of ej omega. I'm looking at x of k, the DFT. DFT of xe of n. The DFT of xe of n is x extended of k, which is equal to summation from n equals 0 up to m, because this one is of m length. X extended of n times e to the minus j 2 pi k n over the length of the sequence m. Now this one looks somehow like this one, but this one is x of n. Now I'm going to take what this extended sequence equals here. So I'm going to do two summations. The first one will be from n equals 0 up to n minus 1, x of n, sorry, x of n e to the minus j 2 pi kn over m And you can put it in a different way. Let me just put it this way. So you have this summation plus summation from n up to n minus 1 zeros times e to the minus j 2 pi k n over m. Yeah? So I'm going to substitute this summation with two summations multiplied by those, and we have this to be the summation of x of n e to the minus j 2 pi k n over m from n equals 0 up to n minus 1. Yeah? I think this one should be inside the summation. So this one here times this, and this one here is also minus j 2 pi nk over m. This one, because I don't want to take the exponential outside the summation because you have an index n here inside, so I'm gonna include them inside. So multiply those by 2, substitute for the extension for x of e, what x of e equals for different values of the indices, and you end up with this one. If you look at this one here, which is x extended of k, it is exactly equals x of ej omega k for the dense grid of m. So we can evaluate x of ej omega at a dense grid of frequencies by zero padding x of n and find the DFT of this extended version of x. So the extended version is only a version of x itself added with 0 added to at the end of it until you reach a value of m. Okay. What I mean here is that you can, if you have a 4, if your n is equal 4, you can 0 pad it with so many values so that your m could be, let's say, 64. You usually have 2 to the power n. M to be a number of 2 to the power n, which is easier for the computer to evaluate the DFT. So we take m equals 2 to the power n. If you take it 64, then you have 4 points, and you add 60 zeros to those 4 samples, so that you have 64 samples, 4 non-zero values, and 60 zeros added at the end. So you have a very dense grid of frequencies, and you can find, when you find x extended of k, it's very close to the continuous domain x of ej omega. If you want to make it more dense and more continuous, looks like more continuous with a very dense grid, then you can say that m, this m can be, let's say m equals 1024, and then you have 4 samples added 1020 points added to 0 added to x of n at the end. You do the DFT of this extended version, and you get very close to the continuous x of e j omega. So this is a really nice relationship, and we do this operation here by adding 0 at the end. We call it 0 padding operation. Okay? So let me just write this down so that you can follow it. So we can evaluate x of ej omega at a dense grid of frequencies by 0 padding x of n to produce x extended of n, and then find x extended of k, which is equal to x of e j omega. Okay. Yeah. So this is a very important result. Probably you may use it in your future life in some projects, doing the frequency spectrum of certain discrete time sequences. So instead of doing the time domain by hand and start to evaluate the frequencies, you can zero pad the sequence as many as you want with zeros, so that whenever you increase, as you increase the number, you find a very dense grid of frequencies, which means that a very excellent resolution of x of e j omega. You know, we just need to mention, when we find for x of n with 4 samples, when we did x of k, x of k had also 4 samples of frequency. So 4 samples are not representative of the frequency domain spectrum of x of n. So when you zero pad those this sequence, then you get a very excellent resolution of x of e j omega. And as long as you increase, once you start increasing more and more, you get more resolution and better resolution, which is something that we need probably in the future. With this, we end up our lecture. Thank you for being with me, and we'll see you in the next lecture. I hope you will find this informative, has some information that you can gain from, and I really thank you.